Section 9.2 is on exponential functions. In the first example, a lot of these examples actually have to do with science. A big thing has to do with population, and there are scientists out there that is their job to figure out how the population is growing, whether we're talking about insects, whether we're talking about people. For the people, actually right now, I've been getting this thing in the mail. It's time for the census. The government needs to know how many people are in your household. They have to have the number of people that are alive and living in the country as well as the world. There's a lot of science examples that throughout this entire chapter. So we'll start off with a happy little example here. And we're talking about these little cutesy little ladybug looking insects that they have pictured here. Here they show you a table, and then they show you this graph. Basically, somebody's little science experiment. Notice that they started out with a population of two. A mommy ladybug and a daddy ladybug, a girl and a boy ladybug. Well, after one day, those two ladybugs, they kissed each other, and by day, after one full day, now there's 6 ladybugs in the little ladybug habitat of sorts. And then things get a little gross from this point, because all those baby ladybugs, then they kissed and they made more ladybugs, so that by the second day, now there's 18 ladybugs in the ladybug habitat. Then after 3 days, then it goes up to 54. It's just absolute incest in this ladybug habitat. Maybe they're not even ladybugs, I don't know. They just look cute with their little polka dot wings. Obviously, insects don't understand the concept of brothers and sisters, but still, the idea is there that obviously these bugs just keep multiplying at quite a very quick rate. That rate is that they keep tripling in size. The number of insects in the experiment multiplies by 3 after each day. So in this function, when you are going to eventually be asked to graph this, none of these populations can start out at 0. There has to be, two beginning, there has to be a starting population in order to get any more additional insects or anything else, animals that we might be talking about. So in the beginning, it doesn't look like it's a real huge one, a huge increase, okay? It's a small increase between 2 and 6. It is a slightly more increase. It's a little bit steeper. And then it really, starts to skyrocket by the 3rd day. You could only imagine how many ladybugs would be in there by like the 10th day. We can figure it out, and we will. There's a little formula to use for that, but they were just kind of showing you what was going on here. But the important part is that you're able to see how they are multiplied from day to day. Now, what makes something exponential and how we're going to look at it, especially with these tables, is that they have to have a common ratio. So you have to identify the common ratio. What keeps getting multiplied? If the population is getting smaller, that means that you have something that is less than 1 as your common ratio. If a population is dying off for one reason or another, that means that it is the common ratio is going to be a fraction of sorts or a decimal less than 1. So you're going to hear the word function rule. That is basically putting an equation in function notation or exponential form. So that form is f of x equals a times b to a power of x. Now only b is raised to that power of x. So don't go multiplying a times b first and then raising it to the power x. That would be incorrect. You must do the b, raise it to the power of x, and then you're going to multiply it by a. So your a is your first term, or whatever the starting population is. In this insect example, our ladybugs, their starting population was 2. The common ratio you are going to eventually have to figure out for yourself, but they were showing us that every day the population tripled. So that is my B value is 3. Now, time, it depends on what day it is that we're going to be talking about. I said, well, let's see how many are going to be in the 10th day. Well, in this example, if I wanted to find out the 10th day, then I would type this into my calculator. I'd put the 10 for the power of x. There is no minusing 1 here. That's something different here. This is just strictly to the power of 10. If I want a different date, I would do that. And on the 10th day, there is 118,098 ladybugs in that little ladybug habitat. It is kind of gross to think about, but your time, your exponent that you are raising the power to. In this example with the insects, it was days. There are examples that we might come across where it might be a number of seconds or minutes. It could be hours. There could be a bacteria, how a bacteria multiplies and more bacteria ends up growing. Again, lots of science here. So it just depends on the problem. Days, years, months, it's just whatever the problem is. We don't do too much conversion, but you should be able to know that there are, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 52 days in a year, and then that's basically as far as we go with that. So time is what the exponent is, and you do not subtract 1 in these questions when you're talking about just the exponential function. We're going to return back to that whole subtracting by 1, but right now make sure you don't get things jumbled up and confused between a basic geometric sequence and this one, because this is just the number, this is the time, and that time includes that that -1, because you're starting at the time would be that you're starting at 0, so you don't really have you're not starting where you have no insects or no people or no whatever. You're starting with a value, so because of that there's no subtracting 1. Okay. Well, while we're speaking of insects, the other big thing is I went online and I was looking at some of these more recent coronavirus graphs, because this is exactly what they're talking about. How many people are getting infected each day. It's not an exact steady increase. You can see because of the scale that they have drawn. This one on the right is it by millions. So it could be, it could have an increase, decrease, increase, decrease. This is just more of an average that it is definitely going up. This one on the right, they started back the number of cases. I think this is the total number of cases in the world, because they're in millions, and I don't believe the United States is quite up there yet. But you can see back in January, there wasn't very much. And then now come April, there's almost, it looks, over 2.5 million cases, according to this table where I got it. I don't know, Worldometers information. I don't even know. They were the most legible and the most relevant to the lesson that I'm teaching now. The graph on the left, again, you see an exponential. Sadly, the United States, we increased. This is a complete exponential function. I mean, it starts off kind of slow, and then all of a sudden, because people are going out, spreading all kinds of stuff, that it just keeps going. What they want to it eventually happen, and why they keep saying flatten the curve, because they want this to take a peak, and then obviously we want to come down at some point. It's going to be a real gradual effect of it coming down. But anyways, what we have so far is definitely exponential. I don't know what the exact rate is. I know my time would be the days. The starting population, I don't know how many we started with in the beginning whenever they started counting all of these cases. But the time would be by days here in order to figure out whatever the exponential function is. But anyways, there's just a little dose of reality and how it relates to the coronavirus, since that's what we're living with right now. All right, let's talk about evaluating an exponential function. Now, these are pretty easy because they give me my exponential function. They tell me that, what are we talking? We got another insect. This is it's the same exact equation we just had. An insect population, you start off with 2. It's tripling. It's being multiplied by 3. Now, what they want is they want to know on the 5th day. Well, just a second ago, I did how much it was on the 10th day. So for this one, type into your calculator 2 times 3 raised to the 5th power. That would be 2 times 243, which gives me 486. So, 486 insects would be your answer. Now, the second one, that we are going to do, the function of f of x equals 1500 times 0.995. Because of this 0.995, they're talking about prairie dogs here. Again, I told you that if that common ratio is less than 1, that's going to tell you that this population is decreasing. Something's going on with the prairie dogs. Maybe they're sick. Maybe they're just not mating like they should be. There could be weather problems. Who knows? Whatever the reason is, people are hunting them. I don't know. But whatever it is, the population is decreasing. So the starting value is 1500. Okay. Now, the decreasing amount is 0.995. That's the common ratio. And they want to know after 8 years. Now, when you go to type this in your calculator, you get a decimal. I'll do it with you. 1500. Go ahead and start typing it in. Make sure that you know how to type this in your calculator. Now, I get a decimal. Now, when we are talking about people, dogs, insects, whatever the case may be. Actually, hold on. I'll write this all in there the way that it shows up in the calculator. We have to do some rounding. Now, if you were a scientist and you had to give, someone the total population of how many prairie dogs there are in this region, you can't give your answer as this decimal because that doesn't make any sense. Looks like there's 1,441 prairie dogs and like a prairie dog's leg somewhere. That miscellaneous leg that might have fallen off some prairie dog does not count as a whole prairie dog. So what I'm trying to get here is that the fact that you need to round to a whole number. And in this case, you are going to round down. So this is approximately, and that's what the little squiggle mark means 1441. You would give 1441 as your answer. You can even cover yourself by just putting the word about in front of it. That's actually even better. But the approximation, which looks like 2 squiggles, is fine as well. But anything basically that has that in any of these word problems, they're not going to tell you to round. It's something that you need to round. You have to know because you can't have a leg of a prairie dog. It has to be a whole prairie dog to count as even if you have a 3-legged prairie dog out there, he's not going to count. So round down is my point here. Even if it was 1441 0.9, you're still 0.9 of a prairie dog. I know that's a lot of prairie dog right there. It still doesn't matter. You're going to you just want to round to the nearest whole number. Okay. So let's look at this one. This one, again, looks like it's reduction, 0.75. So when I do this, I have 8 times 0.75, and I'm raising it. I'm going to replace the value of x with 3. So when I do that, I get 3.375. Right now, we're not going to get an entire lesson on what should I round this to because the directions didn't say. So this one's not bad because it stopped. It didn't keep going, okay? Or you can do the rule of thumb I always told you is that you could say 3.38. Now, this one is acceptable. You don't want to round to a whole number on this one because this one we're talking about a photograph and how large it is. It's 3.38 inches or 3.75 inches. That is totally fine to have that amount. You don't have to have something measure exactly 3 inches or exactly 4 inches. So when I go back to the whole rounding thing, that has to do with like living objects, insects, people, prairie dogs. I think you're going to have one in your homework that has to do with deer, maybe. I think there's one with deer and then there's one with fish, I think, somewhere. But either way, things that are living, you have to round, whereas other things, when they talk about measurements, just keep it the decimal, round to the hundredths place if it kept going. That's okay. Again, you're going to have multiple choice answers, so it's not that terrible. And otherwise, I will clarify. If it happens to be a fill-in-the-blank question, I will say round to the nearest hundredth if it's something with measurement. With a problem like the prairie dog problem, I will not remind you that you have to round it to the nearest whole number. That is something that you just need to know that it gets rounded to the nearest whole number. when it comes to living organisms. Okay, so next we got to be able to identify what is an exponential function based from a set of points. So you want to look for that geometric sequence or that common ratio amongst your y values. Of course, you do want to do a quick check of your x values, but usually they're not going to try and trick you, so you can just write, you can just go starting off with the y value. But if you were out in the real world, SATs or something like this, or in the future when you're in Algebra 2 and pre-calculus, you do want to take a quick check of your x values just in case they are trying to trick you. So the first thing you're going to do is you are going to make a table. So make your little T-chart. I filled in my points already. Step 2, I'm going to look for my x and my y values. First of all, these, my x values, they all increase by 1, so I'm good there. So, or I'm sorry, I didn't mean to put plus signs. I meant to put multiplication signs, that we are multiplying, or in this case, you're not even multiplying by 1, you're just adding 1. I'm sorry. Okay, on the y values over here, we need to see what they are being compared by. Or how do they get? Again, it's multiplication that you want to look for. You're not looking at what the differences are. So here I got 1.5 to 3. That means I'm going to multiply by 2. Next one, 3 to 6 is multiplying by 2, and 6 to 12 is multiplying by 2. Now, if one of those was different from the others, okay, even if one of them I had to multiply by 2.1, that would make it not exponential. So you want to check for your common differences. And once you do, if you, or I keep messing up with the differences, the common ratios. Where did my pen go? Common ratios. Okay. This case, they're all the same. So my answer is yes, it is exponential. And your reason, if you had to explain your answer, is because the y values have a common ratio. All right, next example. First step I have to do is I need to make a table. So I'm going to fill in my points. Now, checking over here on the left-hand side with my x values, these ones this one is just their difference. It's not multiplication. On the right, now I'm going to look. 9 to 9, that means I multiplied by 1. 9 times what gives me 27, and that would be multiplying by 3. And then 27 to 45, that's actually like a weird number because 27 doesn't divide into 45. So you would get times 5/3. Now, the way you'd figure that out in reverse, if you wanted to, you could actually do division. Because if I did 45 divided by 27, 3 goes evenly into both. I'm sorry, 9 goes evenly into both. And that was what would give me 5/3. Either way, even after the first 2 times, once I see the first one was being multiplied by 1 and the second one was multiplied by 3, I could have stopped there. I didn't have to go any further because they all have to be exactly the same. So your answer is no. And because y values do not have a common ratio. So when they ask you to explain your answer, it's one or the other for those situations. It's either because they have a common ratio or because they don't have a common ratio. All right, now we're going to get into graphing. When you're asked to graph an exponential function, you are either going to, for step 1, make a table on your own, just like we were making a table. What you'd have to do here, for example, for this one, you want to pick some points. Again, I'd say 4 to 5 points is what you're going to need in order to plot and actually see that full curve. It's almost like a little bit like a J, but it doesn't scoop back up, but it has to, span a certain part. If you only test out so many points, and when you're doing this graph, and let's say this is it, and you test out just a few, and all you get is a point from here to here, if you did 2 points, you'd have a line. And that doesn't show me that anything is linear for that particular problem. So you may have to do some extra points to see what's going on and to get that entire curve in order to show whatever the problem is. So you make a table on your own. In this first example, the equation was y equals 3 times 4 raised to the power of x. So what you would do to make your own table, pick some points. They pick -1, 0, 1, and 2. Again, 4 points gets the job done on this particular problem. You may be able to get away with 3 points. Probably not. It's probably going to stay around, probably around 4 to 5 points that you're going to have to do in order to get that whole entire curve. So again, you can stick with -2, -1, 0, 1, and 2. They kind of knew that those 4 points would be enough. What you're going to do is then you would type in into your calculator 3. You would type in y equals 3 to the 4th to the -1. Raise the -1 power. Then you're going to do the same thing to a power of 0. Then you're going to do the same thing to the power of 1. And then you're going to do the same thing to the power of 2. We get our y values. And then you go and you plot those 4 points. Connect the dots. Make sure to put arrowheads on each end. Now, look very closely at this. If I can zoom in any further. This red line does not cross the y-axis, okay? It skirts ever so closely, but that's what makes these exponential functions special, is the fact that they don't cross over the y-axis. They're either going to remain above the y-axis or completely below the y-axis. In a second, we'll show you some that have negative values, and they are going to be strictly above or below. That's an important part, because if you had to draw a graph by yourself, and you went to do this, here's my graph, let me get a skinnier pen, and you go to graph this, and let's say you were sloppy about your graph and you did something like this. This would get marked wrong because you crossed over the y-axis. You need to know that exponential functions don't do that. There's no way to get a negative number unless you multiply by a negative number. And the common ratio, if it's not negative, that's not going to happen. So, can't cross over. Make sure you don't cross it over if you draw it by yourself. Okay. Now, the other thing you can do is you can type the equation into your calculator and view the table on the calculator. So I tried taking some pictures here. So you would go to y equals, just like we did before with quadratic functions and linear functions before that. You're going to type in your equation, 3 times 4 to the power of x. You can click graph to see the graph, but sometimes that's not really going to help you if you had to draw this yourself. What you want is the table, because you want to get some points from here. So again, you can take whatever points that you want to get the graph going. If you had to draw, again, multiple choice test here, you can't really draw a graph on quizzes, but at some point in your future, you are going to have to draw a graph of these, and you may have to scale your graph. If we look at the way the book did it up here, notice the scale on the y-axis is by increments of 1, but the scale on the y-axis is increments. It goes 10, 20, or 5, 10, 15, 20. There's little 5s in between. So you may have to do that if you ever were in a situation where you had to draw your own graph. Now, what happens here in this one, both my A and my B are both positive values. So let's take a look at what happens when, here's an example where my A value is negative. So I still have an exponential function, but this one is in the opposite direction. Whatever you had just keeps decreasing at an exponential rate. Again, I can't emphasize this enough. Even though they got the arrow, this would continue out and it would never cross over. It's never going to come up and go in this direction. That can't happen. So it always stays above or below the y-axis. So you'd go about this the exact same way, whether you wanted to type it in your calculator or make a table to get some points. Here's an example where my B value happens to be something that is less than 1. This one, you started up higher and you decrease. Again, does not cross the y-axis. This would come out here and it would never make that cross over to the y-axis. Here's another example of something that's less than 1. Here I have a combination. Not only is my A value negative, but my B value is something less than 1. So this is yet another direction of the graph. Again, if I were to zoom in here, this would continue out. It just keeps getting smaller and smaller and closer to the Y value, but it'll never become 0 and it'll never cross over. Okay. And each one, you would go about the same way, typing it in your calculator to try and go about finding points on the table, whether you want to use the table function or not. Now, for the word problems you really do need to be using the calculator. The numbers, you're going to be using the table. It's just far too difficult or too time consuming, I should say, to do it without a calculator. So in this first example, it says in the year 2000, the world population was about 6 billion, and it was growing by 1.21% each year. At this growth rate, the function f of x equals 6 times 1.0121 raised to the power of x gives the population in billions, x years after 2000. Using this model, in what year does the population reach 7 billion? So, thank God, they give me my equation. So notice they did it for me. They typed it into the calculator. They put y equals, and they typed it in 6 times parentheses 1.0121 raised to the power of x. Now, the calculator, because there's a variable, I'm not solving the equation. I want to go straight to the table. The graph is not going to help me. It's going to be too hard to read. Notice also that they used 6, even though it says 6 billion, and that's because they didn't want to put that many zeros. Because if you were to type this into the calculator, 6, how many? I need 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8. One more. Typing that in the calculator, it's just too big of a number for the calculator to handle. So they just put it in billions, made it easy for me. Now, when I go to the table, I need to get as close as I can to 7 billion. So what they did is they scrolled down. Obviously, you can't have a negative number of years. So they looked at, 1, 2, 3, 4, 5, 6, 7, 8. They kept scrolling down. And then finally, notice it falls in between the 12th and the 13th year. And it does say in about what year. Well, in the 12th year, notice it gets to 6.9316 in the 12th year. I'm not quite there yet. I didn't reach 7 billion yet. So by the 13th year, I did finally reach that value of 7. I went over, but probably like in the beginning of the year, maybe like January, February of this 13th year is when I reached 7 billion, or not I, but the world reached 7 billion. So you want to find the one that it's closest to. And sometimes it could go over, and that's okay. In this case, it was when it finally reached it, and it wasn't quite there in the 12th year. So the answer is the year 2013, because they started this in the year 2000, which they state right here in the word problem. And after looking in the calculator, I can see that it was 13 years later, and that gives me in the year 2013. So that's where they got it from. Okay, now example number 2. An accountant uses f of x equals 12,330 times 0.869 raised to the power of x, where x is the time in years since the purchase, to model the value of a car. When will the car be worth 2,000? Now, difference between these two problems is the fact that right here, 0.869, that shows you a decrease in value. So I started at a car that was worth $12,330. They don't say if it's brand new or the car could be 10 years old at that point. They just want to know, when is it going to be worth $2,000? Maybe they feel like, well, once a car is worth $2,000, just get rid of it. It's pure junk at that point. It's worth more in parts or for whatever the reason is. So what you're going to do first is you're going to type this into the calculator. Type y equals, press the y equals button, and 12,330 times 0.869 raised to a power of x. Even if I put a 0 in there, okay, it's not going to make a difference. I just put 0.869. It'll accept it either way. After you do that, you are then going to go to the table. So you're going to press second, the graph key. Now you're going to scroll up or down to find the value closest to 2,000. Now I tried to make a little video of this using my calculator and videotaping it, but it wouldn't let me insert a video in a video. So I'm showing you a still shot of my calculator. Now notice it started at 4. That's because I scrolled down and I want to get closest to 2,000. So in this particular problem, I'm looking and I want to get closest to 2,000. Now, looks like it falls in between. The 14 is just highlighted because that's where my cursor was. It looks like it falls in between the 12th year and the 13th year. Now, once again, it happens to be a coincidence that the last problem was around the same numbers as well. Absolute pure coincidence that they were the last one was 12 and 13. Yep, and this one's 12 and 13. I guess they weren't really creative with the numbers. That's absolute coincidence. Anyway, so between 12 and 13. If you notice in the 12th year, I'm not at 2,000. I'm at $2,286.7. I'm not quite to $2,000. A little bit more time would have to pass before I'd hit that 2,000 mark. So it happens at some point. By the end of year 13, I'm at 1987.1. So it does occur in the 13th year. So I would say about, or you could say after about 13 years. Again, you could just say about 13 and that's fine. The word about covers up a lot of issues about rounding. We don't need to say, 12.9 or no, it just happens to be, this one is closer to 13 than it is to 12. Also, if you did the math to find out who it's closer to, if I did 2,286.7 minus 2,000, I get 286.7. If I did, for the other one, 2,000 minus 1987.1, what do I get? I'm going to have to do that math. That's a lot of math. Can't think that much right now. Or I don't want to think that much. That's only 12.9, $12.90 away from being $2,000. So obviously you can see it's much closer to 13 than it is to 12. So your answer is about 13 years. Okay, so what I want you to work on right now is on page 628. You're going to do 2, 3, and 4, 2 through 4 all. 5, 8, 10, 14, 17. I kind of wanted to pick and choose. We didn't have to do that many graphs. For these graphs, you can go and you can use graph paper or just use that. You're going to have to scale some of these graphs. I tried to pick some of the ones that had smaller numbers. So you're not having to graph, 108,472. You might have to graph, 52. But in that case, you might have to scale it. So just make sure you can graph those and you can see generally what direction that they go in, or at the very least, be able to type it in your calculator and look at the graph to be able to determine what direction it goes in. That's very important that you're able to do that. Okay, I will see you in Zoom in a few minutes when you're done with those problems.